here we go. We're going to pick up with our discussion of vectors, pretty much where we left off, and talking about the practical real-world applications. Once again, to emphasize, that's what you should be doing all the time. Think about what I put in front of you and where it could go from there, because it's amazing places that the physics can go, and we're starting at the building blocks of it. But if you're already thinking where it's going to go, then you'll do better in this class. And also, as many of you said, you want to go on in engineering careers. Now's a great time to start thinking along those lines. Okay, so here is another example of vector addition with a right angle. So try it. Try to draw yourself a diagram for this, and then try to come up with the resultant. Hit pause, and then come back and see if you got the right answer. Okay, are you back? How did you do? Well, here's my answer. Is that what you came up with? All right. Well, hopefully it is. And let's give another one a try here, too. Now I want to tie in the idea of the one-dimensional motion. We've got the idea here that this is going to be heading off at a particular speed in a particular direction. So now I'm asking you, how far does the boat travel? Okay, in 30 seconds. Why don't you pause and see if you can get the answer that I'm about to show. Was that what you got? 336 meters? All right, well, you're off to a good start then. Okay, here's another one that's at right angles. If you remember when I was talking about the idea of derived units, I mentioned newtons. So we're not really deriving the newton yet, other than what I've already explained to you. But here the N indicates a 15.0 Newton force. So with a 15.0 Newton force, and then we have a 30.0 Newton force acting in at a right angle to the first force. So anyway, just getting you used to the terminology of newtons here. But it works the same way for any physical quantities, and so your right angle trigonometry and your vector addition head to tail is going to work out very well. Give it a try. Hit pause, and then let's see if you have the right answer. And we're back. And here's the answer that I came up with. What is the resultant of the two forces? I came up with this answer here. How did you do? Hopefully, we're on the same page. If not, we can talk about it in class. Okay, let's see what I have in store for you here. All right, one more example here, just to make sure you really know what's going on. Here's another example of two vectors that are going to be at right angles to each other, so a little Pythagorean theorem. And watch pause and see how you do in finding the resultant velocity of the airplane. And we're back. And the answer is, there you go. All right, here I'm trying to keep with the correct number of significant figures. I'm not going to be a stickler for that, but worth pointing out from time to time. 50.0 indicates 3 significant figures. And yeah, so here I'm using 3 significant figures again. Okay, so now we're going to talk about resolution of vectors. Vector addition means that we're going to take one vector, add it to another vector to get a one vector resultant. So we're going to add a number of vectors together to get one vector that is the resultant. In resolution of vectors, we're going to take a vector and split it into two parts, or what we call components. So if you have a scenario like this one, 25 Newton force acting at 30.0 degrees north of west. My question is, what are the northern and western components of this force? What am I talking about? Well, I'm going to give you a diagram to represent this, and here it is. Well, first of all, here are the answers. So we're going to come up with these answers. Maybe even without the diagram, you know what to do. It is a trigonometry problem. But here's the diagram that I promised. Okay, so there is my vector that represents 30 degrees toward the north of west, and there's my 25 newtons, or 25.0 Newton magnitude. Okay, in red and green, reddish and green anyway, I'm drawing the components in the western and the northern direction. In green is the the western component of that force, and then the part that goes to the north is in reddish color over here. So the green is adjacent to my 30-degree angle, and the red over here, the northern component, is opposite the 30-degree angle. So, with a little bit of trigonometry, I can break these into its parts. Since the northern component is opposite the angle, I'm going to use the sine to find out what's going on in the northern direction. Turns out that the sine of 30 degrees is 0.5, so I'll have 12.5 newtons to the north. To emphasize what I've said earlier, you have to make sure your calculator's in degree mode, or you're going to get some answers that aren't going to make a lot of sense if you're in radian mode. Okay, the western component over here, since it is adjacent to the angle, will involve the cosine. So 25 multiplied by the cosine of 30 degrees gives me that western component that I showed you earlier. So there's the resolution of vectors, and we'll be using that a lot. The next thing that we're going to do is add some vectors that don't fit nicely into the nice Pythagorean theorem. They're not at right triangles, but it doesn't matter how complicated the vectors are, we can boil it down to right angle trigonometry. What am I talking about? Glad you asked. Let me proceed. Okay, so here is a person traveling at an angle, and then they're traveling at another angle. This you could draw out as a head-to-tail diagram, do it as a scale diagram, and you could carefully measure things out. Okay, but once you start adding a lot of complicated vectors, it's going to get tricky. The mathematics is the route you want to take, the trigonometry in this case. So here's what I'm going to do in looking for the resultant displacement. I'm going to take each one of these and do a resolution of vectors. Let me show you what I'm talking about. The first vector is 100 kilometers at 60 degrees south of west. So, actually here I tell you what the resultant is. This is the answer that we're going to end up getting, and I'm going to show you how we end up getting that answer. So 219 kilometers at 71.3 degrees south of east. Now let me show you how I did it. Alright, so the first thing that I did is I took that first vector. It's 100 kilometers at 60 degrees to the south of west. So the western component is going to be adjacent. I'll use the cosine. So in the western direction, that first vector is 50 kilometers. Similarly, in the vertical direction, the southern direction in this case, I'm going to use the sine because the southern component is opposite the angle. So the sine is the appropriate trigonometric function. Alright, vector number 2 I can break down in a similar kind of way. It was 170 kilometers to the southeast. Well, southeast is right in the middle of the 90 degrees between south and east, so I will use the cosine of 45 degrees for the adjacent side and the sine of 45 degrees for the opposite side. So there is my second vector and my first vector broken separately into their horizontal and vertical components. Now, in the horizontal direction, the west and the east are working against each other. So the horizontal resultant, you could put it that way, I guess, or the horizontal component of the resultant is going to be 70 kilometers to the east, 50 kilometers to the west, but then back 120 kilometers to the east, netting me 70 kilometers to the east. In the vertical direction, they were both in the southern direction, so I'll simply add them together to come up with 206.6 kilometers to the south. Now, I'm not going to be perfect on these all the time. I'll probably slip up from time to time. But I am trying to do the best I can with the significant figures. Since my initial numbers certainly didn't have 4 significant figures, I'll round that to 207 in my next calculations. Do you see where I'm going with this? Because now I've taken these two more complicated vectors and I've broken them down to components, overall components, that are going to be at right angles to each other. And now I'm right back to my Pythagorean theorem and right in my comfort zone. So here we go. I am going to draw out my 70 kilometers to the east Then I am going to do the 206.6 kilometers to the south, which I'm going to use in my calculation as 207. You'll see that in a moment. And my resultant is from where I started to where I ended up. So I am here. You can see here's where I converted it over to 207. 70 kilometers, 207 kilometers. There's my Pythagorean theorem that's getting me to 219 kilometers that I would have to call the magnitude. And then, since it's the opposite over the adjacent, I'm using the inverse tangent of 207 divided by 70, and that gives me 71.3 degrees toward the south of east, and here is my resultant. The same resultant that I showed you a little while before, but there's the work behind it. Well, I have one more thing to talk about with vectors, and we covered some good ground here already. Hopefully this is all comfortable to you. If not, we certainly can discuss it in class. There's one other way, well, there's several other ways actually, but here's another way that you can be talking about vector notations, and that is what they call unit vectors. So they represent these with the letters I, J, and K. Well, X would be horizontal, Y would be vertical, and Z would be a line coming out of the paper. We don't do too much of that in this class, but it's worth mentioning anyway because the world is three-dimensional, not two-dimensional. But we start off with the basics and then we build up from there. So what does this mean to you? If you have a vector of 3.0i and 4.0j, that just means horizontally it's 3.00 and vertically it's 4.00j. It's that 3, 4, 5 triangle in the end that we talked about. So that's the idea of this one. 3 units horizontally, 4 units vertically. This is a convenient way to add vectors together because if you're adding the 2 here, you've already got the components. So if you're adding up these 2 vectors, this would be my first vector that I mentioned, and here's a second vector that I have going in the negative vertical direction, or negative j. So I would add these up. The horizontals are working together, so I get 5.50. Verticals are working at cross purposes, so I'll subtract off 1.50j. So you're going to see some problems with that notation, and now you'll know what it means. That's about it for my introduction to vectors for you. We'll see how it goes in class. I'll look forward to seeing you there.